Here we have Magnetism FRQ Practice from the Physics Honors Unit 8 curriculum. Here are some important formulas to note. F of B equals Q v B perpendicular, where F of B is the force from the magnetic field, Q is the charge, V is the velocity, B perpendicular is the B field / magnetic field. This will be the most important formula we will be using, as you need to know what each variable stands for and what numbers to plug into each variable. Here we have F of B equals MA, fairly simple. We will be using this in part D. I'll explain it more when we get there, but F of B equals sigma F in the whole FRQ. We can conclude that F of B equals mass times acceleration. Here we have some UCM stuff, uniform circular motion, where centripetal acceleration equals velocity squared divided by radius. We will be using this in part E of the FRQ. Here's a scenario. A proton is traveling horizontally at a constant speed of 4.7 times 10 to the 6th meters per second when it enters a uniform magnetic field of 0.75 Teslas. So here we have a situation. A proton is entering a dot field, which is the magnetic field, and we'll be computing a bunch of different values and figuring out its path. So part A asks us to indicate the direction of the magnetic force on the proton as it enters the magnetic field. To do this, we will be using the right-hand rule as the proton moves towards the B field, which is going to be out of the page since it is represented by dots. So I learned to do this right-hand rule a little bit differently than how the physics teachers have taught. I can link that video from YouTube in this FRQ. I find it to be much more easy, and I will give a brief explanation of how to do it right here. So you will take your thumb and point it in the direction of the proton in which it's moving, which is to the right. So our thumb should be pointed to the right, and the rest of our four fingers will represent the direction of the B field. Since the B field is coming out of the page, our four fingers should be pointing towards us, while our thumb is still pointing to the right. Our palm should represent the direction of the force. Since our palm is facing down, the force from the magnetic field is downwards. This is how we get this vector. On the diagram, draw the approximate path of the proton. Since there's a downwards force, the proton will move in a semicircle in the downwards direction. So this is an acceptable vector, or a line, arrow, whatever you want to call it, that will be on the FRQ, that will be accepted. So this is how to use a little bit of the right-hand rule I briefly described. This is not applicable to this scenario. It's just how to use it, where the palm represents the force, the B field is represented by the four fingers, and the direction is represented by the thumb. I'm sorry that this is not the best drawing. Part C, calculate the magnitude of the magnetic force on the proton. This is where we use the F of B formula. F of B equals Q v B perpendicular. We plug in our numbers. Our numbers were given in the description of the problem. The charge of the proton is on the formula sheet. It is the opposite sign of the electron, 1.6 times 10 to the negative 19th coulombs. So on the formula sheet, you should see negative 1.6 times 10 to the negative 19th coulombs for an electron. So that means a proton is the exact opposite, positive 1.6. So here we have the charge of the proton times the velocity times the value from the B field, 0.75 Teslas. We compute this in our calculator. You should get 5.64 times 10 to the negative 13 newtons. Remember to answer in newtons, as F of B is a force. Part D, calculate the acceleration of the proton. So as the proton enters the B field, we want to figure out the acceleration. Since the total forces of the proton is only F of B and gravity is irrelevant, we can conclude that sigma F equals F of B and F of B equals ma. Therefore, we can derive an acceleration formula from this. So as the proton enters the B field, there is no other force acting upon it other than the B field, as gravity is irrelevant to such tiny objects. FB equals ma, a little bit of algebra, A equals FB divided by M. We plug into the number we already know. So we plug in the numbers we already know, which is F of B. We solved for this in the previous part of the FRQ. And we solve to find A. The mass of the proton should also be given on the formula sheet, which is 1.67 times 10 to the negative 27. This is a value that is on the back side of the formula sheet underneath the constants tab, I guess. So A equals 5.64 times 10 to the negative 13th divided by the mass of the proton. You should get 3.38 times 10 to the 14th meters per second squared. Remember, this is acceleration, so you answer it in meters per second squared. Part E, calculate the radius of the path the proton follows in the magnetic field. So this is where uniform circular motion comes in. As the proton is going into the B field, it will experience acceleration in a semicircle, like we described before in the beginning of the FRQ. So to find the radius, we derive the formula from the uniform circular motion unit, AC equals V squared divided by R. Do a little bit of algebra to solve for radius. We simply plug in our known numbers, and we were given them in the description of the problem, as well as we might have already solved for them. R equals V squared. This was given in our description, 4.7 times 10 to the positive 6 to the power of 2, divided by the acceleration, which we just solved for, 3.38 times 10 to the 14th. We should get a radius of 0.065. Remember to answer in meters. So today you learned how to show your work on each part of the Unit 8 Magnetism FRQ. Make sure you understand how to use all the formulas effectively, and remember the units for each of the values computed. Make sure you know how to use your calculator correctly. Computational errors are common, and use this information to completely and correctly complete the FRQ on the upcoming exam. Please reach out to your teacher if you have any remaining questions. Thank you.